Okay, welcome to Robotics 1. Uh, we have been talking about how to solve homework 4, and in the last lesson, we talked about how to find out the rotation matrices 0R1, how to find out the homogeneous transformation matrix 0H1. Then we talked about how to find out the homogeneous matrix corresponding to mass M1. We talked about 1H2, how to find the homogeneous transformation. Then we talked about how to find out the homogeneous transformation corresponding to mass 2. And then we talked about how to find the homogeneous transformation for mass 3. Now, we derived these matrices and we used them in the equations, and we actually programmed those equations. Now we are at this important step where we have to find out the kinetic energy and the potential energy. So we talked about how to get the positions of mass M1, M2, and M3 from the homogeneous transformation matrices corresponding to the masses M1, M2, and M3. Then please understand, this is an important step, is we need to find out two types of kinetic energies. One is the kinetic energy of translation, and the second one is the kinetic energy of rotation. Kinetic energy of translation and kinetic energy for rotation, these are important because when we use the Lagrangian approach, we will have to find out the Lagrangian. Now, I just want to add one thing. So if you have a rigid body that is rotating and translating in 3 dimensions, then what you want to do is you want to first locate the center of mass. And then the center of mass is going to have a velocity. So I'm going to call this Vg. Velocity is a vector. In other words, it will have 3 components. It will have component in x direction, component in y direction, and component in z direction. Also, there will be rotations. So it will have another vector which I'm going to call omega. Now this will have omega x, omega y, and omega z. Now please understand the difference between the translational velocity and the rotational velocity. Translational velocity is different at each and every point. So for an example, if you look at this point A, its translational velocity is not going to be Vg, but it is going to be Va. And this Va would be different than Vg. However, the rotational velocity at G and at A will be one and the same. So, and this is an important point that you should always keep in mind. So let me emphasize this again. This is the difference between translational and rotational velocities. So if you have a rigid body, the rigid body could have different velocities at different locations, different translational velocities at different locations. But as far as we are concerned, when we try to formulate the dynamical equation of motion, The velocity that we are interested in is Vg, which is the velocity at the center of mass. Now, this rigid body could have rotation about x, about y, and about z. So I'm gonna call this a rotation vector. Let me show this rotation vector. This is the rotation vector omega. It's gonna have three components. It will have omega x, omega y, omega z. And this rotation of the rigid body, whether you consider a point A, whether you consider point B, this omega vector is going to remain same. So it is very important. The velocity in translation changes at every point. But omega, and this is a vector, so it has three components. Omega is same at every point. Now, one classic example is, I want to show you something like, imagine that you have a rod and this rod is rotating at speed omega. Angular velocity is omega. This omega, it's same whether you consider this point, whether you consider this point, this is gonna have same omega. However, if you consider this as a fixed point, say hinge, velocity, the linear velocity at this location, I'm gonna call this location A, is going to be omega RA. The linear velocity at point B, I'm gonna call this RB, is going to be omega RB, and the velocity here, the translational velocity is going to be 0 because the radius is 0. But please understand, the rotational velocity at point O, rotation velocity at point A, and rotational velocity at point B will be omega. Now, the question that arises when we try to solve the dynamics problem, especially when we solve 3D dynamics problem, three-dimensional dynamics problem, is how do we find out the coordinate system? So one thing always remember, for dynamic analysis, Vt and omegas are with respect to fixed or inertial or zero frame or coordinate system. And the reason for that is, if you consider a link that is fixed, if you consider another link and say this link has angular velocity omega, I'm going to call this omega 2. This link has an angular velocity omega 1. So omega 2 is with respect to omega 1, which means if you look at the total angular velocity is nothing but omega 1 plus omega 2. If you look at the angular velocity of this guy, total angular velocity is equal to omega 1. So that is super important. So the next question is, if you have a link, say we were looking at this particular picture, wherein you have a robot, and this robot has 3 axes, and each link may have its own axis that could be oriented differently than the base coordinate system. What I mean by that is x0, y0, and z0 could be oriented differently compared to x1, y1, z1, or x2, y2, z2. Then the question that comes in the mind is what coordinate system we should choose. So the trick here is consider the kinematic diagram of the robot. And you should always consider the kinematic diagram, because kinematic diagram is drawn when the joint angles are 0. So when you draw a kinematic diagram, your joint angles are 0, joint velocities are considered 0, and in the kinematic diagram, you should redraw the 0th frame on the CG of each link. That's what we have done here. And this is an important concept, because please try to understand that you try to work out a problem, and what happens is the robot is shown something like this. And let me show you how the robot would look like. So for an example, the robot is shown in this orientation. So now if you want to solve the problem, let's consider that you have a revolute joint here. Let's consider that you have a revolute joint here. This link is attached to this revolute joint, and there is another revolute joint which is over here. There is another revolute joint which is over here. Now, if I were to follow the guidelines blindly, what I would do is say my 0th frame, just for the sake of discussion. And this is an important point because I have seen students making mistake. So say this is my Z0, this is my X0, and this is my Y0. And what I'm interested in looking at is I'm interested in finding out the IXX, IYY, IZZ for link 2. So the question is, what is the value of IXX, IYY, and IZZ for link 2? So in this case, if I were to blindly follow what we did, then I could just draw my coordinate frame, the 0th coordinate frame, x0, z0, and then y0. But now all of a sudden I have a problem, because this link is oriented at certain angle theta 2 with respect to the base frame. And there is a way to attempt this type of problem, but I wouldn't recommend it. So what you want to do is, this is not the equilibrium position or the position in which you will draw the kinematic diagram. If you were to draw the kinematic diagram for this system, your kinematic diagram should look something like this. So this is the correct way to draw the kinematic diagram. So what you want to do is, you want to consider the link number 2 similar in the same configuration as the kinematic diagram, and then place x0, y0, and z0, x0, z0, and y0. Then you would realize that your major and minor axes for that particular geometry are aligned with x0, y0 and z0. So in this particular case here, they are not aligned. It's not aligned. So what it means, if you try to find out ixx, iyy, and izz, when the link number 2 is oriented by theta 2, most likely your values will be incorrect. So it's always a good idea to orient the link uh, along with the kinematic diagram, and then find out the x zeros, y zeros, and z zeros. But please try to understand your ixx, iyy, izz for each link must be around x0. So you will have ixx, iyy, and izz. So otherwise, your dynamic analysis will go incorrect. Now the next question is, what do we do when the geometry is irregular? So for an example, here is what happens. And this is actually quite common. So for an example, is you have a robot arm, and that robot arm is maybe some complicated shape, something like this. And that robot arm is actually a three-dimensional robot arm. And practical robots are not going to be regular, but they are going to be of some weird shape. Its CG will be somewhere here. So this is G. Now, how do you find out IXX, IYY, and IZZ for such a complicated geometry? Now, first and foremost, we don't try to find out IXX, IYY, and IZZ using the manual technique. One way to solve this problem is we try to approximate this with some regular shape. Say we consider this to be a slender rod, or we consider this to be a plate, and then we try to find out IXX, IYY, IZZ using the, the, the mathematical equations that we derived. But most likely, what we do is we find IXX, IYY, and IZZ using some sort of numerical technique. And we don't actually program in Mathematica or MATLAB. We use a CAD software like SolidWorks or maybe AutoCAD or Fusion. And what we do is we try to find out something called principal moment of inertias. And what is the concept between principal moment of inertia? Principal moment of inertia is actually called a tensor. So this is called as the tensor. And it has 9 elements. So it has 9 elements. So you have x, y, z, x, y, z. Now you're gonna have, this may sound a little complicated, but it is really not. So consider that you have your IXX, IYY, and IZZs. So think about it like you have IXX, IYY, and IZZs. And on off diagonal terms, you have IXY. Please note, same thing here, IXY. Then here you're going to have IXZ. Here you're going to have IXZ. Here you're going to have IYZ. And here you're going to have IYZ. So these are the main component on diagonal, and you are going to have some off diagonal component. These off-diagonal components indicate that the moment of inertia is not aligned with the principal axis. So what I mean by that is, consider you have a link, and this link has CG as shown location. And then there is going to be some axis, I'm going to call this X, Y, Z. And if you find out the moment of inertia about this particular axis, then you will have off diagonal terms at zeros. So if you find out moment of inertia about the principal axis, then you are just going to have Ixx, Iyy, Izz, and all other terms will be zero. But for some reason, if you were to find out the principle of the moment of inertias about some other axis, if you find moment of inertias about some other axis, I'm going to call this X bar, Z bar, and Y bar, you will have off diagonal terms. And when we try to look at uh, the moment of inertias, we are always looking at principal moment of inertias, which means you should be looking at the inertia matrix where the off diagonal terms are zero and you just have the diagonal terms. And these are the terms that we found out when we were trying to find out I1, I2, I3. So this was Z naught, this was X naught, and this was Y naught. For the problem in homework 4. And this concept is slightly tricky to look at, but as far as we are concerned, we are going to study regular bodies in robotics 1. So we will look at slender rods or the rectangular shapes or the regular shapes. So we are going to have the principal moment of inertias. Our off diagonal terms are going to be zeros. But when we go to robotics 2 and when we will actually come up with the dynamic analysis for a robot arm, a practical robot arm, in that case, we will go to the CAD model using in SolidWorks. We will look at the different inertias that are reported by the CAD software and see which inertias to pick. So this is super important that depending upon the axis that you choose, your moment of inertias would be different. So coming back to the point that we were discussing, if your robot is shown in an inclined shape, the first and foremost thing to do is convert or imagine that robot in its equilibrium where all the thetas and theta dots are zeros. Look at the kinematic diagram and use that as the reference to find out moment of inertias. Everyone understood this? This is an important concept. And this is needed before we proceed to the kinetic energy. So this is what we found out in last class. For link number 1, our Ixx1 is 0, Iyy1 is 0, Izz1, Iyy1 is I, and Izz1 is I1, Ixx2 is 0, Iyy2 is I2, Izz2 is I2. For link number 3, Ixx is 0, Iyy is I3, and Izz is I3. Now, our task is to find out the total kinetic energy. Total kinetic energy. Now the total kinetic energy is, you have the kinetic energy in translation, and then you have kinetic energy of rotation. Now kinetic energy for translation is very simple. So you have the mass of the link m1, you have the velocity vector that you have found out. So what I'm going to do is, I'm going to square the velocity vector. I'm going to square the velocity vector and then multiply that by mass m1 and 0.5. And when I do that, I have the kinetic energy of translation. So this equation translates into 0.5 m1 v1x square plus m1 v1y square plus m1 v1z square. Now, please understand, and this is an important distinction between the rotational kinetic energy and the translational kinetic energy, is that mass is same whether you are multiplying with v1x square or v1y square or v1z square, your mass is always going to be m1. However, for kinetic energy of rotation, you have Ixx, Iyy, and Izz. So let's see what happens for link 1. For link 1, I'm going to represent this as 0, I1, I1, and I'm going to have this multiply with omega x1 square, omega y1 square, omega z1 square, and whole thing multiplied by 0.5. Now please understand, this is the dot product between two vectors. So I have, when I expand this, I'm going to multiply this. I'm going to write this over here, 0.5, 0 multiplied by omega x1 square plus I1 multiplied by omega y1 square plus I1 multiplied by omega z1 square. And the difference here is, this is very important, is the term multiplying the angular velocities in x direction, y direction, and z direction are different. So in other words, when you are trying to find out the kinetic energy of rotation, what you should do is, you should have Ixx, Iyy, Izz for that particular link. Say if it is link number 1, and take a dot product with omega x1 square, omega y1 square, omega z1 square, and then multiply that by 0.5. And this is something that we will use when we try to solve the problem. Last but not least, and I need to clarify this, when you are trying to find the potential energy, you should always find out the potential energy in the direction gravity is acting. So for an example, the problem that we are solving, is, this is the direction in which the gravity vector is aligned. So you would be looking at PZ1, PZ2, and PZ3. These are the positions about Z. But in certain cases, depending upon how your robot is, you could have your other axis oriented in the gravitational direction. Say for an example, if you have y0 that is oriented in the direction of gravity, in that case, when you try to find the potential energy, you should be looking at Py1, PY2, and PY3. Any questions here? So please keep these ideas in mind when you try to work out the problem. And now what I'm going to do is I'm going to share my MATLAB screen, and we will go back to the code that we are working on. So now you should be seeing my MATLAB screen. So before I proceed any further, I just want to make sure that we are clear with the code. Line 1, forward kinematics. In line 2, we are clearing everything. We are clearing screen in line 3. Line number 4, we are defining the symbolic variables theta 1, theta 2, theta 3, theta 1 dot, theta 2 dot, theta 3 dot. Line number 5 to line number 11, we are defining the masses m1, m2, m3, gravitational acceleration. Then we are finding out I1, I2, I3. Please note I1 is same as IYY1, IZZ1, IXX1 is 0. Then I2 is IYY2, IZZ2, I3 is IYY3, IZZ3. Then we did homogeneous transformations. So we derived the homogeneous transformations and we programmed those here. Please note, these are the homogeneous transformation relating to frame 0 to frame 1. Line number 17, homogeneous transformation from frame 1 to frame 2. Line number 18, the homogeneous transformation from frame 2 to frame 3. Please note, these are not the homogeneous transformations for masses. These are the homogeneous transformation for frames. And this is what we need to solve inverse kinematics problem. So to find out H02, which is the homogeneous transformation of frame 2 corresponding to frame 0 with respect to frame 0, is given on line number 20. Line number 21, we have H03, which is the homogeneous transformation of the end effector with respect to 0th frame. And this is what we will use. H03 is to be used to solve inverse kinematics. The next part of the code is we need to find out the positions and velocities of masses m1, m2, m3. In this particular problem, mass m1 is at the center of link 1. Mass m2 is at the center of link 2. Mass m3 is at the center of link 3. So please note that these lines are modified. So this tells me that this is the position of the mass. Similarly, I made the changes in the second homogeneous transformation for the mass 2. But now what I need is I need the location of mass 2 with respect to the 0th frame. That's why I have this equation, wherein H01 is multiplied with HM212. For the third mass, M3, I do the same thing, L3 by 2, L3 by 2, and I find homogeneous transformation for mass M3 with respect to 0th frame. Then I get the values of the individual positions for masses. And please note, when I'm finding out the positions, I'm looking at these homogeneous transformations and not the homogeneous transformations on line 16, 20, and 21. Once we are done, we grab all the homogeneous transformations for the masses. We get their x positions, y positions, and z positions. Next thing is I want to find out the velocities of mass m1. And here I'm using a trick shortcut. I'm finding the Jacobian of m1 px, m1 py, m1 pz with respect to the joint variables theta 1, theta 2, theta 3. And the Jacobian is the velocity of mass m1 is Jacobian multiplied by the derivative of joint variables. Same thing we did for mass m2. I found the Jacobian corresponding to m2 py x py pz t1 t2 t3, and then I found out the velocity of mass 2. Same thing we did for mass 3. And once I got these values, finding the linear translational kinetic energy is very simple. What I did, I squared each velocity vector. So each term in velocity vector was squared. Since m1 is multiplying all those terms, m1 is remaining same, I just multiplied with m1. Same thing I did with m2, same thing I did with m3, and then I multiplied the whole term by 0.5. So at line number 74, I have the kinetic energy of translation. Now the next question is, how do you find out the linear Jacobian? Please note, to find linear Jacobian, you need to get H03. Should not take Jacobian, the H03 for mass M3. So you will take H03. This is the position of the end effector with respect to zeroth frame, X position of the end effector, Y position of the end effector with zeroth frame, Z position of the end effector, and then I have T1, T2, T3. That gives me the linear Jacobian. Now, this is the part which needs a little bit of discussion. So, omega 1 is R00. This is R00 multiplied by 00 TD1. That is the angular velocity of link 1. Angular velocity of link 2 is omega of link 1 plus H01. Please note, this is H01. This is the rotational matrix relating 1 to 0. So, and this is what we found out earlier. If you go back to the code, we found out this over here. Then for angular velocity of link 2, you will have angular velocity of link 1, then multiplied by 00 TD1. So this gives you the angular velocity of link 2. And the angular velocity of link 3 is nothing but this angular velocity, which is the angular velocity of link 2 plus H02 00 TD3, which is theta 3 dot. Now, some of you may ask me, why don't I have H03? And the reason for that is because we don't have theta 4. We don't have theta 4 dot. That's why if you think about what H03 is, and I want you to think about it in a little bit in the physical systems, from physical systems point of view, H03 is giving me the relationship between the angular velocity or the position of the end effector with respect to the zeroth frame. But what I'm interested in the angular velocity of link 3 that is dependent on the previous transformation. That's why I have H02. And this is very important. Please check. TD2, which is theta 2 dot is multiplying H01. R, and if you look at, so R00 is multiplying with theta 1 dot. R01 is multiplying with theta 2 dot. R02 is multiplying theta 3 dot. So, and at this point, we have information to find the Jacobian. And so for Jacobian, I actually used a MATLAB function which is called equation to matrix, where you have omega 3 and then you have TD1, TD2, TD3. Now I just want to confirm that you have the same relationship and your code runs. So if you say JWW, that should give you the Jacobian for the angular velocities. Any questions at this point? The next part is interesting. Now, what I want to do is, I want to find out the total angular kinetic energy. So to find total angular kinetic energy, I'm gonna write the equation here and then I will explain what this equation does. And I will put the same equation in the chat window. So if you look at this equation, this is the total angular kinetic energy. What I have here is I have Ixx1, Iyy1, Izz1 multiplied with omega xx1 square, omega yy1 square, and omega zz1 square. So this is actually a dot product that I showed a minute ago. So if you want to just grab this, copy, I'm going to type it over here, paste, and I'm just going to evaluate. So what happens is, this gives me, this is actually 0 multiplied by omega x1 square, Iyy multiplied by omega y1 square plus Izz1 multiplied by omega z1 square. Same thing I'm doing for the link 2. For link 2, it is Ixx2, Iyy2, Izz2 multiplied by the square of the angular velocities. Now it is actually, I need to show you something. So first and foremost, let me write down, or let me just show you what is omega I2. Can you see omega I2 is actually a vector, which means it has 3 elements. It's a vector. It has 3 rows and 1 column. Now, if I were to do omega I2 square, please note there is a dot operator. This dot operator, what would this dot operator do? Check this out. This dot operator would take each element and square it. So TD2 sine theta 1 got squared, minus TD2 cosine T1 got squared, and the last term is TD1 that got squared. Now what I want to do is, I want my Ixx2 to multiply this term plus Iyy2 to multiply with this term plus Izz to multiply this term. So what I want is, so let me just show you what is happening. II1, II2, II3. So, and what I want to do is II1, then II2, II2, and II3. Just assume I want to multiply with So now check what happened, that these terms II3 got multiplied with TD1 square, II2 got multiplied with this, and II1 got multiplied with this. So what happened, that these two vectors, when we took the dot product, I got just one element, one row, one column. So this vector equation got converted into a scalar equation. So, and please note, kinetic energy is a scalar quantity. It's not a vector quantity. So you are multiplying with these two vectors, and now you have an energy scalar quantity. Same thing here. This is the angular kinetic energy of the second link. This is the angular kinetic energy of the third link. Any questions at this point? The next step is, I want to find out the total potential energy. The total potential energy, I'm gonna copy this over here, and I will actually send this in the chat window. So please take a look. This is M1G, M1PZ that we got from the homogeneous transformation matrix for the first mass. M2G multiplied by M2PZ that we got from the homogeneous transformation for the second mass. M3G, M3PZ, which is the Z, the displacement in Z direction for mass M3. Once we have that, we are ready to form the Lagrangian. And please note, we have two kinetic energies and one potential energy. So I'm going to state my Lagrangian is kinetic energy of translation plus kinetic energy of angular velocity. So, and then minus the potential energy. So when I do the Lagrangian, I have this. Now what I need to do is I need to add the syntax to come up with the code to find the Euler-Lagrangian. So, and that syntax we are familiar with, but still let me go through this. First, you want to define the states, and please note the code requires these states to be defined in certain order. Here, your symbolic variables are T1, T2, T3, TD1, TD2, TD3. That's fine. But when you define the states, they should be the state derivative of the state, state derivative of the state, state derivative of the state. So T1, TD1, T2, TD2, T3, TD3. Now please note, there are three masses, which means you are going to have three internal forces, you would have three external forces. In this particular problem, you do not have any external forces or any internal forces. Now, if there were forces, how would you find these? So for an example, if you want to find out either external forces or internal forces, remember, we have already derived the equation. That is nothing but Jacobian transpose multiplied by the force at the end effector. So if there are any external forces, and if you want to find out if you need to provide those, this would be the Jacobian transpose multiplied by the force at the end effector. There is no energy dissipated in damping, so zero, and there are no parameters. And then we can use the command to generate the function, the Euler-Lagrange function, and that is Euler-Lagrange LXQIQERP mod M, because you want the MATLAB script, and ODE1. The next thing is we add the delay. And then for homework 4, we add the delay so that the code is generated. And then the next step is the time span is from 0 to 1 second. I'm going to paste it over here. And then we need to supply the initial conditions. So initial conditions are given in the problem. And please note, MATLAB requires the angles in radians and angular velocities to be in radians per second. So my first theta, theta1 is 0. Theta1 dot is 10 degrees per second. So I converted that into radians per second. Second theta is 45 degrees. So I converted that into radians. Second theta dot, theta2 dot is 0. Theta3 dot and theta3, they are 0. And then I'm just constructing initial conditions for numerical integration. So this is how it is done. And then I will invoke the numerical integration code ODE45. So I'm gonna copy and I'm gonna paste it over here. Now what I'm gonna do is I'm gonna copy this and paste it in the chat window. And then I will paste the last part in the chat window. Now, if you followed so far, then at this point, you should have your code completely done. Now, next thing is just click on the run and wait for the code to execute. And now I got some results. So what I'm going to do is I'm going to show those results. And these are the results of what I got from numerically integrating the differential equation of motion. You can clearly see the robot is unstable because there is no controller, because displacement T1 as velocity is changing, the displacement continues to grow. Displacement theta 2, again, that starts with 45 degrees and goes all the way up to minus 200. Displacement T3 starts, or theta 3 starts with 0 and goes all the way to minus 150. And you would see this type of behavior. You will see in velocities, theta 1 dot is minus 10, is sort of oscillating, going back and coming back, going up, coming down. Then theta 2 dot, starting from 0, it kind of oscillates back and forth. So it kind of becomes like sort of a pendulum. Theta 3 also behaves something similar to a pendulum, wherein the velocity increases, decreases, then continuously increases, and kind of drops down. So that is how your code should run. At this point, I would encourage you to run this code on your own MATLAB command and tell me if you get the same results. Any questions, concerns? Okay, now I'm gonna go back and change. Just a second. I will go back to my code. Okay. Graphs in degrees. in radians. That's fine. So if you look at the way I'm drawing here, my graphs are actually in degrees too. My graphs are in degrees and degrees per second. So your graph and my graph should be same. It doesn't matter if you have your graphs in degrees or radians, the trend will look the same. Only thing, the scaling factor is going to be different depending upon whether you have in radians or whether you have in degrees. Okay, Trenton, do you have any question? Line, so this is. So here is, I'm just, if you look at the chat window, I have line 100 in the chat window. So just go up and you should be able to copy and paste from my chat window. Okay, any other questions related to this code? Okay, so this concludes the dynamic analysis, and please note that you will be doing something similar in your last quiz as well. So please try to understand this material carefully, and when we study robotics 2, we will use again Lagrangian approach to derive the equations of motions for complicated robots. So make sure you understand this three-dimensional dynamics. The only thing I want to emphasize at this point is this. In the problem that we have looked at so far, we did not add any external force. If there is an external force, this is the place to put it. If you have an external force, this is the place to put it. Now, some of you may ask me, how would this work? Remember, we have Jacobian transpose multiplied by F at the end effector. So this is, so if in any problem, if there is an external force at the end effector and you are asked to find out the differential equation of motion, then you will be writing that over here, QE. So your external force will be the Jacobian multiplied by Jacobian transpose multiplied by the end effector force. And we spent a lot of time on this when we looked at the Jacobians and we derived the equations, but that is something that you wanna keep in mind. Okay. So motor forces are actually torques, T1, T2, and T3. And yes, that is where the torques go, T1, T2, and T3. That is where, if you have motors supplying the torques, that is where you would apply the torques. Now here is something I want you to be super careful. This code or this formulation will not work when your motor torques are changing with respect to time. So let me clarify what I mean by that. And I haven't worked out a problem on that, but I don't intend to do this in robotics 1, but we will do that in robotics 2. So if you look at this, the code, the way the Euler-Lagrangian and the way the ODE1.m is formulated, let me show you what I mean by that. Just a second. If you look at this ODE1, it does not give you a direct option to add the external torques. So what you will want to do is you will have to go to this code and manually change this last line. This line number 63 needs to be changed manually so that you can have time varying torques in the picture. So for an example, think about it like you have 3 motors. Motor 1 is supplying a torque, say 10 sine t, where t is changing from 0, 1, 2, 3, 4, 5, 6, which means that value of torque gets updated in every iteration of this script. So at every time step, you have a new value of torque. That does not work in this code. So if you add, for an example, say let's take an example and you will see what I mean by that. If I say sine t, what this means is I have a motor torque that is changing in a sinusoidal fashion. Now, if I run this code, see what happens. If I run this code, it gives me an error. So you may say, oh, there is a problem because it doesn't find the variable t. And what I'm going to do is I will add SYMST and try to run it and see what happens. You still have an error. And now this error is in VF Euler-Lagrange. So which means now the error is at this location. Error is at this location, which means the error is in Euler-Lagrange. Euler-Lagrange is not set up to handle time varying torques. Once again, Euler-Lagrange is not set up to handle time varying torques. Let me tell you what this means. Just wait a second. So now what I did is I went back and actually I changed the time to a constant. And let me show you my results. So when I supplied torque as a constant value, say 10, the equation ran. But when I supplied torque as sine t, the code gave me an error, which means that the Euler-Lagrange equation, the formulation, the way the code is written, is not set up to accept time varying torques. There are two ways to handle this. Either you can use the parameters, but when you use parameters, then please note that your MATLAB code, you can use parameters, but then your MATLAB code will get changed. And then you cannot use this syntax. Or what you can do is to handle time varying torques or time varying forces, you can directly go into ODE 1 and check this out. You will have to modify this last line of your code. You have to modify the last line of your code, and then you should be able to handle the time varying torques. Any questions? So, and again, don't be intimidated by this super long expression. This actually expression, when you start working on this code, that is not that complicated. Any other questions? Okay, unfortunately, I don't have enough time to start the next topic. So I'm gonna stop here, but I would be happy to answer any questions you may have related to the robotics one, or in general, any questions related to the material. Robotics Toolbox, you can use Robotics Toolbox. Let me stop recording for a second.